In 1892, Alexander Gleason released his new standard map of the world as it is, which remains to this day one of the most accurate flat Earth maps ever created. He had hopes it would completely replace globes and Mercator maps the world over, but unfortunately his map's influence was short-lived. The next year, in 1893, Gleason published his flat Earth tome entitled Is the Bible from Heaven? Is the Earth a Globe? Does Modern Science and the Bible Agree? Which gave many flat Earth proofs and also explained his wonderful map.
First, I want to say thank you to Flat Earth Banjo, USA, Japan, and Brazil for sharing this beautiful Gleason's map. In the descriptions below, you can find a link to his channel and some other great Flat Earth channels as well. During my videos, I'm going to answer some frequently asked questions and explain every detail of this Gleason's map. The last few weeks I met some wonderful persons on the internet, and one of them, Fritz, asked one of the most frequently asked questions, and that's to measure the distance from Sydney, Australia to Perth. I also met a wonderful person, his name is Hashmal Dawn, I hope I'm pronouncing it correct, and he wanted to know the distance from Sydney to Chile, Santiago de Chile. So I'm going to explain two flight routes, one from Sydney to North Pole and from North Pole to Chile, and one is circumnavigate to Chile. So let's start with the first one. Fritz asked this question from Sydney, Australia to Perth, Australia. So first we have to find Sydney and Perth. So let's zoom in and have a look. Oops. Yep. Yeah, as you can see, this is Sydney. It's written here, Sydney. To Perth, Australia. It's there. But first we need to find the latitude and the longitude coordinates. From the meridian of Greenwich, it starts at 0. These are the longitude lines from 0 to 180 degrees. This is the east of Greenwich, and from 0 to 180 degrees, this is the west of Greenwich. It's also written on the map. And clockwise is west of Greenwich. It's also written on the map. So from the equator, everything above the equator is positive, and everything latitude below the equator is negative. So this is 15 degrees between these two lines. This is the 30 and the 45. So the best way is to divide the 15 degree line in 15 degrees. So I'll show you the best way to do it. So let's say these are the latitude lines. Latitude between Sydney is between 30 and 45. The best way to do it is to divide the distance in 5 equal size pieces. 1, 2, 3, 4, and 5. It means if this is 0, this is 15 degrees, between 0 and 15 degrees. 32 to 45. It means this one is 3, 6, 9 and 12. So if I divide each these in three equal size pieces, I'll get a pretty accurate measurement. So this one will be 1, 2, 4, 5, 7, 8, 10, 11, 13 and 14. That's the way we're going to do it on a piece of paper. I'll show you. Now we're going to do the same on the map. Make sure you don't write on your map. So between the lines, and now we have to divide it by 5 equal size pieces. So this is the 0, it's 15, 3, 6, 9, 12, and then 1, 2, if you're not satisfied, you can try it again. When you're satisfied the way you divide it, you can cut it and use it to measure the other distances as well. So I hope you can see it. It's from the 0, it's 15 degrees plus 15 degrees plus 4 degrees. That's exactly where this, it's just about, yeah, let's say 4. So now we have our first coordinate, that is 34 below the equator. It's minus 34 because we are below the equator. So if you're above the equator, to the north, we say it's a positive. Below is negative. This is very important. These are not scale to measure distances or degrees between the latitude lines. We have our piece of paper to measure between the latitude lines, the degrees between the latitude lines, but these are 1892 conversions. I will explain this later. Okay, so let's find our longitude coordinate for Sydney, and in this case you need a strong piece of string. I prefer to use dental floss. You can also use a piece of nylon. What you need to do is to put a string on the center of the map and then make sure you're on the longitude line, make sure it's center, and then move the string down until you reach Sydney. Then you can read the degree on the circle, on the map, and it's 1. So this one is 151. This is the 150 mark plus 1 degree. Each longitude line is separated by 15 degrees. So this is 5, 10, 15, and each one is 1, 1 degree. So it's 1, 2, 3, 4, 5, and then 10, 15. So make sure you're on the center of the map and then move the string until you reach Sydney, and then you can read the degree on the map. I have to zoom with my remote and also show you on the map. So I will place a magnet in the center of the map to hold the string, and then I can zoom in so you can have a better look. So I place a magnet to hold my string, and let me zoom in for you. Check if you're on the, make sure you are on the longitude line. Yeah, I hope you can see it. And from there you can measure until you reach Sydney. Approximately there. I'll show you. There is it. This is the line. So it's approximately, let's say 51 for the purpose of our explanation. I place a marker so you can see Sydney. There's a small circle there. On the longitude line, be sure the line is straight to the center, and then move the string until you reach Sydney. And you can read the degree on the circle. It's 150 plus 1 degree. So I'll place a marker. So now we have the coordinates for our first location, Sydney. The latitude is -34, longitude 151 east of Greenwich. So now we have to find the coordinates for our second location. So we have the same piece of paper dividing the latitude lines in degrees. So each one of them is 50 degrees. And now we're going to measure the distance to Perth. This is the equator. And from the equator it is 15 plus 15 degree plus a few more degrees. And that's why we need our piece of paper to measure the distance to Perth. If I put it this way, so it's 15 and 15 is 30. This is the 30 degree line latitude, and a few more degrees to reach Perth. Let me zoom in so you can have a better look. So it's somewhere between 1.5 and 2, but for the purpose of this demonstration, let's say it's a 2. So from equator to Perth is 15 degree, 30 and 2 degrees. So it's 32 latitude below the equator. So if I move it like this, I will reach Perth at around 10, sorry, this is 5, 10. So this is 105 plus 10 degrees. So Perth is on the longitude line, 105 plus, this is 5, 5, 5. This 15 degree. Each longitude line is divided by 15 degrees. So this is 10, so 5 and 5 is 10 degrees. So this is 105 plus 10 degrees, 115 degrees. Okay, the next step is to measure the distance between Sydney and Perth. I placed a marker on the 115 degrees for longitude line for Perth, and I placed another marker for Sydney at 151 degrees. To measure the distance between Sydney and Perth, we need to know how many degrees are between Sydney and Perth. We have our longitude for Sydney, it's 151. Each longitude line is separated by 15 degrees, so this is 15 plus 15 is 30 degrees, plus 5 is 35, plus 1 degree is 36 degrees. So between Sydney and Perth we have 36 degrees. The real distance between Sydney and Perth is 36 degrees. That's the amount of degrees between Sydney and Perth. Multiply by 60 nautical miles. Why 60 nautical miles? To answer this question, we have to read between the lines. And it says 60 miles to the degree. It means for each degree is in reality 60 nautical miles. So the total distance between Sydney and Perth is 2,160 nautical miles, and we need a modern conversion to convert it to kilometers, and that's approximately 4,000 kilometers. So I hope I answered the question, and I have to say the Gleason's map is scientifically and practically correct. In the next video, I'm going to answer the question to measure the distance from Sydney to Santiago de Chile. Thanks for watching. In this video, I'm going to show you how to calculate and measure the distance from Sydney to the pole and from the pole to Santiago, and to circumnavigate from Sydney to Santiago. At the end of this video, I'm going to show you that it is possible to calculate a straight path from Sydney to Santiago. But I will show you in another video how I did it. Don't forget to check some great flatter channels in the descriptions below. Again, the Gleason's map is scientifically and practically correct. I had a wonderful discussion with this person on the internet. His name is Hashmal Don, and he wants to know the distance between Sydney, Australia and Santiago de Chile. In the first part of my video, we found the coordinates for Sydney, and we're going to do the same for Chile. But let me zoom in and see if we can find Chile. This is Chile, and we need to find Santiago de Chile, is the capital Santiago. Santiago is not written on this map, but there's another city, Valparaiso, and Santiago is west of Valparaiso. So I see a dot, a circle, a very small circle here. So I suppose this is Chile. But for the purpose of our demonstration, we can assume that this is Chile, and we'll use it as Chile. In the first part of our video, I showed you how to find the coordinates for Sydney. We measured them and we pinpoint Sydney, and we found the location, the coordinates 34 and 151. So let's find out the coordinates for Santiago. We don't really need it to measure the distance from Santiago to Sydney, but for the purpose of our demonstration, let's just measure coordinates. Let me zoom in. As you can see, Santiago is between two latitude lines. This is 30, between the 30 and the 45, between these two. I hope you can see it, yes. So we have to measure the distance in degree from Santiago to the 30 latitude line. Let me put a marker. So there it is, to pinpoint Santiago. And the first part of the video, I still have my scale. So we're going to measure how many degrees are between Santiago and the latitude line. Well, let's say 3. I hope you can see it. 3 from this small circle to the latitude line. We measured 3 degrees. That's from latitude line. This is the 30 latitude line plus 3 degrees. It's 33 degrees below the equator, minus 33. The latitude is minus 33 west of meridian of Greenwich. Now we're going to measure the longitude line for Santiago, and our marker shows that Santiago is between the longitude 60 and the 75. So Santiago is somewhere in between. So I have my piece of string. I prefer to use dental floss. So let's measure the longitude and let's find out. So I will zoom in later, because first I would like to measure it from the center. Make sure it's on the longitude line. I hope you can see it. Keep it stretched and then move until you reach Santiago. I hope you can see it. It is somewhere between 71.5. Looks like 71.5. I hope you can see it. I will zoom in, but first I have to hold the center with a magnet so I can zoom in for you to see. So I placed a magnet on the pole to hold my string. Can you see it? Yes. Yeah, this is it. I placed a magnet to hold my string, and now we're gonna measure. Just check. Oh, yeah, just check if it's on the right spot, on the center, and then move until you reach Santiago. And it's about 5. It's 65, 70, 71.5. Well, for the purpose of our demonstration, we say 71.5. I hope you can see it. It reached Santiago 71.5. Let me hold this one and move the camera so you can see the magnet. There's my magnet. Dawn's question is to measure the distance between Sydney and Santiago de Chile. We're going to measure the distance from Sydney to the North Pole and from North Pole to Santiago de Chile. And the next one, we're going to measure the distance from Sydney, circumnavigate to Santiago de Chile. In this case, it's going to be easy because we know our coordinates, we know the locations. So the only thing we need to do is to measure how many degrees lies between Sydney and the North Pole and from the North Pole to Santiago de Chile. We know Sydney is 34, so at the 30 latitude line plus 4 degrees, and Santiago de Chile is on the 30 latitude line plus 3 degrees. So we can measure all the way up to the North Pole for both locations. Sydney. From the North Pole, it's 1, 2, 3, 4, 5, 6, 7, 8 plus 4 degrees. So it's 84 degrees from Sydney to the North Pole. From the North Pole to Santiago de Chile, it's 1, 2, 3, 4, 5, 6, 7, 8 plus 3 degrees. From the North Pole, all the latitude lines. This is the equator. From the North Pole, you have 15 degrees and then 15 degrees, 15, 15, 15, 15, 15, 15. So it's 1, 2, 3, 4, 5, 6, 7, 8. 8 times 15 degrees plus 4 degrees to reach Sydney. Let me put it this way. From the North Pole, 1, 2, 3, 4, 5, 6, 7, 8 plus 3 degrees to reach Santiago. It means the distance from Sydney to North Pole, it's 8 times 15 degrees for each latitude line plus 4 degrees to reach Sydney. That equals to 124 degrees times 60 nautical miles makes a total of 7,440 nautical miles. We do the same from the North Pole to Santiago de Chile. The distance is 8 times 15 for the latitude lines. It's 8 times 15 plus 3 to reach Santiago. That makes a total of 123 degrees. Multiply it by 60 nautical miles and you get the real distance. That's 7,380 nautical miles. So the total distance from Sydney to Chile is 7,440 plus, that's the distance from Sydney to the North Pole plus the distance from the North Pole to Santiago de Chile, and that makes a total of 40,820 nautical miles, and that's 27,464 kilometers. The question is, why 60 nautical miles? To find the answer, we have to read between the lines, and it says 60 miles to the degree. It means for each degree is in reality 60 nautical miles. Scientifically and practically correct. To navigate from Sydney, Australia to Santiago de Chile, we have to count the amount of degrees between Sydney and Santiago de Chile. That's 1, 2, 3, 4, 5, 6, 7, 8. So it's 8 times 15 degrees. Each longitude line is 15 degrees plus 14 degrees. This is 5, 10, 11, 12, 13, 14, because this is 1 degree. And on the other side it is 1, 2, 3.5, because the other way is 71.5. So we have to add 3.5 on this side and 14. That makes a total of 14 degrees plus 8 times 1, 2, 3, 4, 5, 6, 7, 8 plus 3.5 degrees. You get the total amount of degrees. To circumnavigate from Sydney to Santiago, it's 14 degrees plus 8 times 15 degrees for the nautical miles plus 3.5 degrees to reach Santiago. That makes a total of 137.5 degrees. 137.5 degrees multiplied by 60 nautical miles, that makes a total of 8,250 nautical miles. That's 15,279 kilometers. These are the distances I calculated from using the Gleason's map from Sydney to Santiago, from Sydney to the North Pole, and from North Pole to Santiago. This is the distance I calculated to circumnavigate Sydney to Santiago. And if you fly in a straight line, this is a flat plane, the distance will be shorter than 8,250 nautical miles. These measurements are based on the Gleason's map. I showed you how to measure distances using the Gleason's map. You can measure latitudes, longitudes, but you cannot measure in a straight line. Of course, you can fly straight to Chile, but you cannot measure a straight line. You cannot, because the Gleason's map is not scaled that way. It's a different ratio. You can only measure using the longitude or the latitude lines. And like I said before, this is not a scale to measure from one place to another. This is an 1892 conversion. By using this, I calculated a direct flight from Sydney to Santiago in a straight line. At this moment, I'm just showing you the calculations, and in my later video I will explain it, because you won't be able to understand it at this moment. Some globe believers think when you fly from Sydney to Chile, you fly like this. In reality, you fly like this. But if you believe you fly like this, whatever makes you happy, as long as it's a safe flight. Ashmal done. I hope I answered your question. Thanks for watching. This is the third video, and in this video we're going to find a flight plan from Sydney to Tahiti. Don't forget to check the descriptions below for some great flat earth channels. In this video I'm going to find a flight plan from Sydney to Tahiti. In my first video I showed you how to measure and find the coordinates for Sydney using some tools, and we're going to do the same for Tahiti, and then we're going to find our flight plan from Sydney to Tahiti. First we have to find Tahiti and see if we can find Tahiti. So there it is, Tahiti. The question is a flight plan from Australia to Tahiti, and we're going to use this Gleason's map to demonstrate how to do it. The Gleason's map is a flat earth map. I will make a few more videos explaining a lot of details of this beautiful map. Now we have found Tahiti. Let me put a marker. So there it is, Tahiti. We're going to measure the latitude, and then we're going to measure the longitude line. Let's start with the latitude. From the equator, the 0 degrees, we have the 15 degrees latitude line or circle and the 30 degrees. Tahiti is between the 15 and the 30 degrees. So we have to measure how many degrees Tahiti is from the 15 degrees. I have my same scale. You can watch my previous videos. I explain this very detailed. As you can see, we divided latitude lines in degrees, and for Tahiti we have to measure we have to place it in the right spot. I hope you can see it, and you can measure. It's approximately between 2 and 3 degrees. Let's say 2 degrees. So it's 15 degrees plus 2 degrees. That makes it 17 degrees. That's our first latitude below the equator. So it's a negative number. We found our first coordinate for Tahiti. That is 15 degrees plus 2 degrees. It's 7 degrees below the equator. It's on the latitude line. West of meridian of Greenwich. Next, let's find our longitude coordinate. Therefore, my favorite tool, Dentafloss. It's a strong piece of string. Place it to the center, exactly on the center. I hope you can see it. Make sure you're on a longitude line, and then move it until you reach Tahiti. You have to move it just a little bit. As you can see, this is 1 degree, this is half a degree, so this is approximately a quarter of a degree. It means this is 150 degrees minus a quarter of a degree. That's 194.75. That's longitude minus 149.75 west of meridian of Greenwich. That's why it's a negative number. But I can even say it's west of meridian of Greenwich. Let me explain it this way. If we fly from Sydney all the way to Tahiti, we circumnavigate. When we reach the 150 longitude mark, we haven't reached Tahiti yet. We still need to fly a quarter of a degree to reach Tahiti. To find our flight path using the Gleason's map, we have to fly from Sydney. We are going to fly straight on the same longitude line north until we almost reach the latitude to bring us to Tahiti. So the latitude is the same, and from here, when we reach 17 degrees, we fly east on the same latitude and we reach our destination. The question is the next coordinates to turn east. Let's find out. From Sydney, we have to fly on the same latitude north until we reach latitude minus 17 degrees. That's the same latitude of Tahiti, and then we have to fly east to reach Tahiti. It means the longitude is the same as 151, and from this, at this moment, we have to turn right, east direction, same latitude, and we will find our way to Tahiti. This is the latitude and this is longitude. This is east meridian of Greenwich. We can also measure the distance from Sydney to this location, our turning point. First we have to fly north, and when we reach latitude 17, turn east, and we can also measure from this location to Tahiti. The latitude, the difference is in latitude, and from this one we can measure the degrees between the two longitude coordinates. To be more accurate, we can say it's 14 degrees plus 3 times 15 degrees plus a quarter of a degree to reach Tahiti. So because it's a small distance from the 150 longitude line to Tahiti. Like we measured 149.75. So we have to add another quarter of a degree to reach Tahiti. But for the purpose of our demonstration, and we can get let's say it's on the 150, so it's easy to calculate. It's 15 plus 14 degrees. It means we have to fly 16 degrees north. That is 16 degrees times 60 nautical miles. That makes a total of 1020 nautical miles. 1020 nautical miles north, and from this position we have to turn east, and that's 3 times the longitude lines plus the 14 degrees to Sydney. That's 59 degrees. 59 degrees times 60 nautical miles, that makes a total of 3,540 nautical miles. The total distance from Sydney to Tahiti is 4,560 nautical miles. Why 60 miles? To answer this question, we have to read between the lines. And it says, "60 miles to the degree." 60 miles to the degree. It means each degree is in reality 60 nautical miles. The Gleason's map is scientifically and practically correct. This is the flight plan from Sydney to Tahiti. These are the distances I measured from Sydney to Tahiti, flight plan, longitude and a straight path, the internet distances I found, and it looks like the world is shrinking. Well, I can't find North Pole on a Google map, so I guess North Pole doesn't exist anymore. Who knows? Thanks for watching. In this video, I'm going to explain the sun based on the Gleason's map. As you know, the Gleason's map is scientifically and practically correct and was used in England, Canada, France, Denmark, Sweden, Germany and Australia. I hope this video will be very interesting for Marilyn's Spirit Level channel. She is a great flat earth activist. You can find the link to her channel in the descriptions below and some other great flat earth channels as well. The sun is one of the most important things in life and also one of the most important things on this map. Welcome to the flat earth. Unfortunately, I cannot say let's start with a common knowledge, so I'll say let's start analyzing the Gleason's map. At 12 o'clock noon, that is at the meridian of Greenwich, the zero longitude line, the sun rotates around the pole and completes its cycle within 24 hours. That's one day. According to the Gleason's map, the sun rotates around the pole. The time is written on the map, Greek numbers, from 12, 1, 2, 3 o'clock, 4 o'clock, until 12 o'clock night, and then from the morning back to 12 o'clock noon, when it reaches the meridian of Greenwich the next day. The sun does not only rotate around the pole, but during the rotation it narrows its path to the Tropic of Cancer, then continue to rotate and widening its path to the Tropic of Capricorn. It means during the seasons the sun moves between the Tropic of Cancer and the Tropic of Capricorn, and on the 21st of December it reaches its peak, and on the 21st of June its peak on the Tropic of Cancer. The sun travels around the circle in 24 hours time. The circle is divided in 360 degrees. It means the sun travels 360 degrees in 24 hours time. That means the sun travels 15 degrees every hour. So this is 6 o'clock, 7 o'clock is 15 degrees, and then 8 o'clock is 15 degrees, another 15 degrees, 10 o'clock, and so on. Let's measure the latitude coordinates for the Tropic of Capricorn and the Tropic of Cancer. But before that, let's have a look at another wonderful feature of the Gleason's map. December solstice. The sun is on the Tropic of Capricorn. The 21st of December it reaches its maximum, and you can also see where the sun illuminates the area. Again, the Gleason's map is scientifically and practically correct, and it's written on the map: on December the 21st, the sun moves around the Tropic of Capricorn and during the day lights up the southern portion of the Earth from the Arctic Circle to some portion of Antarctic ice. There is no sunlight, and sunlight is between quotation marks here, beyond 80 degrees south, but unknown region of ice. On the 23rd of December, the sun commences his northwards journey again, returning to his starting place, and thus completes his season. June solstice. The sun is on the Tropic of Cancer, and on 21st of June it reaches its maximum, and you can also see where the sun illuminates the area. The Gleason's map is scientifically and practically correct. It's written on the map. In the figures June and December, the white represents the sun's position in its respective month at noon. This shows sunlight inside the Arctic Circle for 24 hours. From June 21st, the sun moves round the tropic in a spiral circle, widening every day until it reaches its destiny on the southern or outer solstice on December 21st. It's written on the map: the sun moves. Scientifically and practically correct. Let's measure the Tropic of Capricorn. Can you see it? This is a 15 latitude line plus 5. It's 20, and then 21, 22, 23, and just a bit over the 23. So it's between 23 and 24. It's just over the 23 mark. And the Tropic of Cancer is also between 23 and 24. This is the 20, 21, 22, 23. As you can see, the 9 is 24, but sits between the 23 and the 24. I measured the Tropic of Capricorn between 23 and 24 degrees. Tropic of Cancer also between 23 and 24 degrees. So I had to search the internet and found it should be 23.5 degrees. Let's find out what the Gleason's map has to say. This is one of the most important things of the Gleason's map, the sun, and is also one of the most important things a flat earther should know. The sun is one of the most important things in life, and it's one of the most important things on this map. This is a zoom-in situation from the seasons, the sun, the solstices, and the key of some secrets. So let's get started. The Gleason's map is showing us that the sun rises from the east, and during the seasons it moves from the north and the south, between the north and the south, between the Tropic of Cancer and the Tropic of Capricorn. This is the equator, the middle. The equator, Tropic of Cancer and the Tropic of Capricorn. and this is the equator. If the sun rises from the east and moves during the season between the south and the north pole, why is the north pole on the right? Because if the sun rotates around the pole and I can see the sun rises from the east, that means the north should be on my left hand side and the right south. But on the Gleason's map, the north is on the right hand side. This is one of the greatest secrets of the Gleason's map, and I'll explain it in the next video. The sun rises from the east and travels during the seasons between north and the south. That means between the Tropic of Capricorn and the Tropic of Cancer. The sun travels 30 degrees to the tropic to the north and 30 degrees to the south. It means the sun travels between 30 degrees north and south. This is the 15 degrees, 30 degrees, 45 degrees. I am not looking at the longitude lines. This is a triangle and this is an inverted triangle. It's the same triangle, the zero. This distance, the size, the distance is the same. Let me do it like this, maybe you can see it. This is 90 degrees, this is 90 degrees, and this is also 90 degrees. So it's the same triangle, same distance. This is 0 degrees, 15 degrees, 30, 45. It's an inverted triangle, so it's the same distance from the sun. On the equator is 0, 15 degrees, 30 and 45. So the sun travels 30 degrees until it reaches the summer or the winter solstice. The same on both sides. The center is the equator. So this is the equator. The sun travels from between north and the south. This is a quick drawing from the Gleason's map. The sun is at the equator. It's 0 degrees. That's why the equator is 0 degrees. And measured from the sun is 15 degrees, 30 degrees, 45 degrees. The equator is 0. This is not a latitude line. I'm just showing you the degrees measured from the sun. So if the sun is at the equator, it's 0 degrees, 15 degrees, 30 degrees. So if the sun travels during the seasons between the south and the north, it reaches the 30 degrees. If we're standing on the ground and look at the sun, we say, well, it's 90 degrees. And on the 15 degrees, it's 75 degrees. And on 30, it's 60. That's why this is not a latitude. Not only that, the distance between 15 degrees and 30 degrees and 45 degrees is not the same. It means if the sun is 15 degrees, if we measured the angle to the sun, we measured 75 degrees. And when the sun is 30 degrees, if we measure the angle, we measure 60 degrees. Because this is 90, we measure 60 degrees. But when the angle measured from the sun is 45 degrees and we are at latitude 45, we also measure 45 degrees. That is why this is very important, the latitude 45. Because the equator is the 0 and the latitude 45 is the latitude 45. But the 15 and the 13 is not the latitude because this distance is not the same between 15 degrees, 30 degrees and 45 degrees. But the 0 is the same, the sun is straight above our head, is 90 degrees. From the sun it's 0 degrees. And when the sun is 45 degrees, if we are on latitude 45, we also measured 45 degrees. So this is very important. Let me draw an equator and explain more on an equator line. Okay, this is the latitude. This is the latitude. This is the sun's degree, 15, 30, but on 45, the angle of the sun is the same as the latitude. So if the latitude is 45 and the 0, the equator, they divided it in 15 degrees, equal size degrees, and the 60, etc. So the 15, 30 is not the same, but a 45 degree is also the angle of the sun. So at 45 degree, if we are on latitude 45 degree, if the sun is at the equator, we measure the angle of 45 degrees. This is very important. We know the importance of the 45 degrees. This is the latitude. The equator, 15, 30, 45. Equal size pieces. So this is the latitude. Equator is very important. The 45 degrees is very important. And it's just divided between equal size pieces. The question is, where is the 23.5 degrees? The Gleason's map is telling us when we are at the equator, the sun is 30 degrees, we're looking at the sun, let's say this. This is also 30 degrees. If the sun drops on exactly the 45 degree line, we will look straight at the sun at an angle of 23.5 degrees. So this is the 23.5 degrees. It means if we are on a 45 degree latitude, we're looking direct straight to the sun as well. This is what the Gleason's map is telling us. Let's go back to our Gleason's map and I'll show you all the details. Marilyn, please pay attention. This is the equator. This is the 45 degrees latitude. Let's follow the 45 degrees latitude and see where it takes us. It brings us at the base of the triangle, the center, the equator. between the Tropic of Capricorn and the Tropic of Cancer, the 45 degrees latitude. If the Sun is at the Tropic of Cancer or Capricorn, and you are at a 45 degrees latitude, you will see straight at the Sun at an angle of 45 degrees. This is 45, this is also 45, from the 45 degrees when the Sun is at the equator, and it tells you it is also 45 degrees. You're looking straight at the Sun if you are on the 45 degrees latitude. This is also the 45 degrees latitude. It is the same as when the Sun is at the equator. When the Sun is at the equator on the 45 degrees latitude, is 15, 30, 45, also on the 45 degree latitude, you will look at the Sun at an angle of 45 degrees. When you are at the equator and the Sun is 30 degrees, that means on the Tropic of Cancer or Capricorn, you will look at the Sun at an angle of 23.5 degrees. This is the 23.5 degrees. The Gleason's map is perfect. It's a masterpiece. It's a masterpiece. Scientifically and practically correct. I draw on my map just to show you, but you don't have to do that. You can use a piece of string, strong piece of string. I use dentifloss, and you can also measure the degree. If you stretch the string exactly to the center of the Sun and the center of the small circle, it measures exactly 23.5 degrees. 23.5 degrees. Let me zoom in, see if you can look at it as well. Let's go back to our drawing board and I will show you exactly how it is mathematically. I made a quick, beautiful drawing. This is the Sun. This is the equator, the 45 degrees. The Sun. When the Sun is at the equator, the angle is 45 degrees, looking straight at the Sun. When the Sun moves to the 30 degrees, Tropic of Cancer or Capricorn, it will reach to 45 degrees, and you're still looking straight at the Sun, like the Gleason's map showed us. And if you measure this angle, it will measure 23.5 degrees. This is a beautiful example. An A4 piece of paper, folded and makes a perfect square. This is a perfect square. It's a square. Measure the 30 degree line. This is the 45 degree line, where the 30 degrees crosses the 45 degrees, exactly at that spot. If you measure the angle, it will measure 23.5 degrees from the equator. This is my beautiful sun. And the beauty of it, exactly in the same spot. Marilyn, now we know the importance of the equator, the importance of the 45 degrees latitude, the importance of the 45 degrees, the importance of the sun, the importance of the pyramid. Do you see what I see? Do you see it? Perfect triangle, equator, latitude 45, the base is flat and level. One thing is sure, everything is measured from a flat plane. The triangle and the sun. It's flat. The base is flat and level. Scientifically and practically correct. 1 degree is in reality 60 nautical miles. The 0 degree angle measured from the sun is the 0 degree at the equator. The 45 degrees measured from the sun is the same as the 45 degrees measured at the latitude 45 degrees. It means if we know the distance from the equator to the 45 degrees latitude, then we know the distance from the base to the top. It's written on the map, 60 miles to the degree. It means 1 degree is in reality 60 nautical miles. 45 degrees times 60 nautical miles. Scientifically and practically correct. Thanks for watching, and I'll finish this video with some beautiful observations. Back in those days, people tried to get a picture of the flat plane by drawing it on different kinds of maps and sizes. And then came someone with a brilliant idea and created the first 3D model to give a full view of the vast plane. The born of the first 3D virtual reality model, the globe. Today it's still written on the globe, not for educational purposes. Well, but Gleason's had a different view. I think he was not only a genius, but he was an artist and created this beautiful masterpiece, the Gleason's map. Today I'm going to reveal the secrets of this Gleason's map. Welcome to the Flat Earth. In my last video I asked the question, if the sun rises from the east, why is the north on my right? Well, Gleason was an artist, and like any other artist, he hid Waldo in his art. Can you see Waldo? As it is, between quotation marks. To understand the Gleason's map, we have to understand the reality. Let's start with the reality. This is the Bonneville Salt Flats. Okay, I know, this is my whiteboard. Let's assume it is the Bonneville salt flats. And three friends decided to start a warehouse business and decided to share this space into three equal size spaces with equal space in between. And one of them, Fritz, came with this idea. Vast open space, the salt flats, the three friends back to back, and this divided the place into different sections. Empty space for their privacy, each size, and this is the space they're gonna use for the warehouse. So this is Banjo, this one is Fritz, and this one is me. For the example, let's say this is 1 yard and it goes endless, as big as the salt flats. Fritz started immediately with a 1 yard wooden box with a bicycle in it. He placed it here, 1 yard. Then he got a 10 yards car, a 50 yards boat, and a 100 yards train. As you can see, smaller objects use less space and bigger objects use more space. So it goes from smaller objects and gradually to bigger objects, because you cannot put a 100 yards train in a 1 yard space. That's impossible. In the reality situation, it's impossible. The smaller the object, the closer to the center. The bigger the object, the further away, because the space grows gradually. After a while, my space was full, and Banjo's warehouse, one box of 30 yards and one 50 yards. But something is bothering Fritz, because he thinks it's not safe. We agree, and we decided to hire a security guard to guard the place. So we created doors for the security guard to walk through the warehouses. So he can walk in and walk out all around the place. At the same time, Fritz wasn't happy because he had no clear view of the situation and he couldn't figure it out how to manage the whole system. So we agreed to hire someone to solve the problem. Luckily, Banjo had a friend and his name is Gleason, and he came to solve this problem, to register the whole system so we can have a clear view of the whole area. And this is the way Gleason's solved the problem. He drew a circle and divided it in degrees. And he said 1 degree is in reality 10 yards. 1 degree is in reality 10 yards. And he said, what if I draw an object here? What size is this object? Fritz is a great mathematician, and he said, well, that's easy. It's 10 degrees. If 1 degree is 10 yards, it means it's 10 degree times 10 yards is 100 yards. Correct. Well, Gleason said, what if I draw the object here. Again, Fritz said, if I measure 10 degrees, it means 1 degree is in reality 10 yards. So I have 10 degrees. So the answer is 10 times 10 is again 100 yards. Okay. Gleason asked for the third time, what if I draw the object here? Fritz said, okay, measure it, and he said, well, it's 10 degrees, so again, it's 10 degrees times 10 yards is 100 yards. Correct. But this time, Gleason draw a second object. And he asked Fritz, what is the size of this object? Fritz said, well, if I measure 5 degrees, this is 5 degrees. So in reality, this object is 5 times 10 yards is 50 yards. Correct. If you look at the size of both objects, the 100-yard object looks smaller than the 50-yard object. But it doesn't mean it's not correct. Because if you measure it, it's the correct size. This is 100 yards, it's 10 degrees, and this is 5 degrees, it's 50 yards. So it matches the reality. It's correct. It's what you measure. It's not what it looks like, it's what you measure. If you measure 5 degrees, it means it's 50 yards. If you measure 10 degrees, it's 100 yards. And that's the size of the object in reality. Gleason's look at the reality, and he said, position 3, I have a 1-yard bicycle. Position 2, a 10-yard car. Position 1, a 50-yard boat. Position 0, a door on both sides. Position 1, a 100-yard train. And then he went back to his drawing. Position 3, I have a 1-yard bicycle. Position 2, a 10-yard car. Position 1, a 50-yard boat. Position 0, a door on both sides. Position 1, a 100-yard train. Gleason's managed to map the whole Bonneville salt flats, the whole flat plain, in one circle. The whole flat plain in one circle. But Gleason said to the security guard, remember reality. The reality is, when you walk in the warehouse, and if you want to go to the smaller objects, follow the N. Go to the center. If you want to go to the smaller objects, go to the center. Follow the N. And that's what he did on his map. If you want to go to the smaller objects, follow the N. It means if the sun rotates clockwise and you are facing the sun, the N is on your right. That's what Gleason said on his map. If the sun rises from the east, you face the east, the N is on your right. In the reality situation, if the security guard walks in, the N is on his right. But this is the reality. So if you want to follow the smaller objects, if you want to go to the smaller objects, you have to go to the right. You have to follow the N. Now this is very confusing. Am I saying the north is on the wrong side? No. I'm saying be aware of the reality. Am I saying the largest countries are at the center of the Gleason's map? No. I'm saying you have to think about it. Am I saying the Gleason's map did it the same way I did it here? No. Because the Gleason's map used time zones, coordinates, latitudes, etc. It's not the same. I'm saying you can map a whole flat plane in one circle. A whole flat, level, endless plane in one circle. The reality is you can measure everything from the true center. Not by the degrees, but by the angle of the true center and the distance to the objects. This is the reality. You can move the larger objects that are further away from the center to the center. They are still visible. But the smaller objects will become invisible. And the smaller objects at the center will become more visible. But the reality is, if you know the angle between the objects and the distance to the objects, you can calculate the size of the object, of each object. This is the reality. We know between the 45 degrees, Tropic of Cancer and Tropic of Capricorn, between the 45 degrees, it's flat and level. Let's do some measurements and see if it makes sense. Let's start with the first one. From Sydney to Tahiti. I did 5 measurements. The first one, from the center, the latitude degrees to Sydney and latitude degrees to Tahiti, and the angle between Sydney and Tahiti, and calculate a straight line from Sydney to Tahiti. This is the result. The second one, from Sydney to Tahiti, the latitude degrees to the minus 90 degrees from Sydney and to Tahiti, and the angle between Sydney and Tahiti. This is the result. The third measurement, I measure the distance to the center for both Sydney and Tahiti, and then the angle between those two, and use the conversion to convert it to nautical miles, and then 60 miles to the degree. If you have an A2 size map, I did the measurements as well. The fourth measurement I did from Sydney to Tahiti, and then use the conversion to convert it into nautical miles, the legend to convert it into nautical miles. And the last one, the fifth one, I measured just the degrees and then add 60 miles to the degree. Like some of you have noticed, this is not the correct answer. These are the results. None of them makes sense. Not even the last one, which is the closest one. The Google distance is way too short compared to all the measurements. The second one, from the minus 90 degrees, is not correct, and the fifth one is also not correct. Let's remove it. And then I realize I can't believe what I'm seeing, and it's not because of the glow. The next measurements are from Sydney to Perth. The distance we measured from Sydney to Perth, nautical miles and in kilometers, and this is the distance in Google, kilometers. Wait a minute, is this a coincidence? Let's measure Greenland. These are the results. Greenland from east to west, the width using an A1 format map. These are nautical miles, kilometers, and I also found World Atlas size is 1276 kilometers. Google Map is a question mark. I showed you all the calculations. I showed you how to map the whole flat plane in one circle. And the reality is, if you know the true center and the distance to the objects, you can calculate the size of the object. You know the angle, the distance to the object, you can calculate the size of the object. That's the reality. Did Gleason made a copy of the globe? Maybe he did, but I don't see a curvature between the 45 degrees latitude line on his map. It's clear a curvature between equator and the 45 degrees latitude. On Gleason's map, between the 45 degrees latitude and the equator, it's flat and level, the base of the pyramid. Now you know where this symbol came from. Flat, level, plane. The sun is the most important thing. This is the triangle. Everything can be measured by using the triangle. The base of the triangle is flat and level between the 45 degrees latitude lines. The sun is one of the most important things in our life. One circle.